Problem. All
Okay, so
right.
we're going to go ahead and get started. So again, I'm Joe Deli
Great.
Carpini, the Science and Operations Officer, and Bryce Williams, one of our meteorologists, is with me to help with tonight's presentation. So again, this is Weather Models 101, and Bryce, I will hand it off to you to get us started.
All right. Sounds good. Well, thank you everyone for joining us. Sorry it's a little late, but I'm here. So let's talk about weather models. If you are a weather enthusiast and you followed our forecast office on Twitter or Facebook, or before that, and even now, you read our forecast discussions on our website, then you have heard lots of talk about weather models or guidance, we'll call it sometimes numerical guidance. And so this is a little bit about I'm going to start off with a little bit about the history of what that means. So numerical weather guidance is basically just the use of mathematical models of the atmosphere to predict the weather. So this is a picture of some of our supercomputers that we have at our headquarters in Silver Springs, Maryland. And we're always continuously funneling tons of data from satellites, radars, observation networks, all sorts of things into these supercomputers that are then running trillions of calculations per second, way more than we could ever hope to do, and spitting out what's known as computer guidance. And so later on in the presentation, Joe's going to get a little bit more into the details of what that looks like, but I'm going to start with some of the history of how we got here. So hope you guys like a history lesson because you're going to get a lot of history here. So going back to the very beginning, the roots of the numerical weather prediction came from somebody who, as a meteorologist, we are familiar with the name. I believe I pronounce it Bjerknes, Wilhelm Bjerknes. Joe might correct me on that, but I'm
That's
going to stick
correct.
with it.
No, you got it.
Okay, good. So he was a Norwegian physicist, and he has been called the father of modern meteorology. And that is for a reason. Back in 1904, he published a paper that suggested that it would be possible for us to forecast weather using a complex system of nonlinear partial differential equations. And that brings back some PTSD from me from just thinking about differential equations class in my undergraduate years. Not fun, but important for figuring out what exactly the weather is going to do. And he had that idea first. So we need to talk about a British mathematician, Lewis Fry Richardson, who spent 3 years developing Bjerknes techniques to solve these equations. And so you can see here on the right some of the primitive, quote unquote, primitive weather forecasting equations that we use. And if you are a weather nerd like us, or you ever go to school to be a meteorologist, you'll become familiar with a lot of these equations. But back then he had nothing more than just a slide rule and a table of logarithms, and so he was working along the World War II battlefields in France as a member of the ambulance unit when he was doing this. And so he computed a prediction for the change in pressure at a single point over a 6-hour period. This calculation took him 6 weeks to do, and also the prediction turned out not to be realistic. But so that seems like a fool's errand, but his efforts were a glimpse into what was possible in the not too distant future of weather forecasting. So this is actually very interesting. This was the first that I had when we were putting this together. This was the first I had seen of this, and it is fascinating. So Richardson first saw a quote unquote forecast factory. And in this, he calculated that 64,000 human computers, each responsible for a small part of the globe, would be needed to keep pace with the weather in order to predict weather conditions. So these human computers, would be housed in a circular hall like a theater with galleries going around the room and a map painted on the walls and ceiling. And a conductor would be located in the center of the hall, coordinating the calculations using colored lights. Wow, that is lofty vision he had. don't think that we ever made it to anywhere quite like that, but it is a cool concept to think. And you know, he was at least, you know, willing to step out of the box, I guess.
And Bryce, that was the original weather forecast office, I think. So
that was the original weather forecast. That would be something, wouldn't it? It looks more like a coliseum.
And I'm glad we have computers. That's all I'll say.
Seriously. So next we have, moving right along in the history books, we have John von Neumann, and he developed the first computer called the ENIAC, E-N-I-A-C, and that would recognize that the problem of weather forecasting was a natural for this computer, this newfangled thing called a computer. He is the first one who had the epiphany, you know, maybe this is the answer to how we can actually do this instead of a big globe with lots of people in it. So in 1948, he got together a group of theoretical meteorologists, which that already sounds very difficult, theoretical meteorologists, at the Institute of Advanced Study in Princeton, New Jersey. So this group was headed by a guy named Jules Charney, who had done extensive work on developing a simplified filtered system of equations for weather forecasting. So altogether, they constructed a successful mathematical model of the atmosphere and were able to demonstrate the feasibility of what we know as numerical weather prediction. So the first one-day nonlinear weather prediction was made in April of 1950. So its completion was not simple. It required round-the-clock services of the modelers, and because of the several ENIAC breakdowns of the computer, you know, having issues, more than 24 hours to execute. But this forecast was successful in proving that the weather community could use computers and numerical weather prediction to make their weather forecasts. So then stepping up into the 1950s, 1954, modeling capability and computer power were advancing to a point where it was actually possible that real-time operational NWP or numerical weather prediction would be feasible and under consideration not only in the United States but also in Europe. So in July of 1954, the Joint Numerical Weather Prediction Unit was organized and staffed and funded by the U.S. Weather Bureau, the Air Force, and the Navy. And so this new unit was given the mission to apply emerging computer technology to the operational production of weather forecasts. And you can see a picture here on the right. Fred Schumann and Otha Fuller in 1955 at the IBM 701, which was the first computer used by this Joint Numerical Weather Prediction Unit to produce operational numerical weather prediction. All right, so eventually technology advanced and advanced, and so we had a progression of more and more powerful computers that were gotten by the National Weather Service into their hands and able to be used for NWP. And so through the 1960s and 70s, we not only got better computers but also increasing sources of data because we had new sources like satellites, which allowed us to expand not only the domains of the models, but the number of models that were run. And I'll explain what domain means here soon. So these increases were not only made in the scope of the domain, which is basically, you know, the area that was covered by the model, but also we were able to increase the number of vertical levels and horizontal resolution of the models. So it created basically a 3-layer hemispheric model in 1962 and a 6-layer primitive model in 1966. So just ever increasing, you know, I know that this is kind of a lot of jargon, but basically we were just ever increasing the complexity and the detail that went into these models. So what that does for us is all of these models become better and better at giving us an idea of what the atmosphere is going to do. So the model is doing the math calculations for us. It is taking what we call initial conditions, so the observations, you know, how cold, how hot it is, how much moisture there is, all that kind of thing, and it is using that as initial conditions to run these equations and give us graphical output. And that's what we look at as the forecaster. We're not looking at the equations, we're looking at the graphical output by those computer models. So these global models typically run 4 times a day, and there's all sorts of models, and we'll explain the details of a handful of them, but they all have different resolutions, initial conditions, parameterizations, and schemes that make the output different. So this is kind of a global 3D view of the idea of these models sectorizing the atmosphere all around in not only a XY plane, but a Z plane. So horizontal, but also vertically. So you can see it's basically splitting up the atmosphere, this layer of the atmosphere all around the whole globe into grids. So not only horizontal grids, but vertical grids. And the smaller the grid, the better resolution, spatial resolution that the model has. So I talked about earlier about model domains. So what I meant when I was talking about the domain is the area on the globe that this model is capable of forecasting for. So this area of focus, basically. So the global models, they can forecast and focus on the entire globe or one hemisphere of the globe. Then we have regional models that take smaller sections within that hemisphere or within the whole globe, like whole countries, like the US, which would be like the North American model. Then you also have mesoscale models. Mesoscale is just meaning even smaller sections, like a part of the country, like the Northeast, like you see here. And we'll talk about what some examples of each of those are. So these global models, they focus on the large features like jet streams, cyclones, highs and lows, and things that affect a large portion of the globe. So the input from the global model initializes regional models in order to give them a starting point. So it feeds into our smaller domain models to give them something to start with for their forecast. It also feeds into climate models these models are modeling long-term, months, years in advance, and provides forecasts out to several weeks, at least, or at least gives us outlooks out to several weeks. These are all initialized with the global model domains. So then downscaling a little bit to the regional models, so say the one that covers all of North America here, these are able to provide much more detail for large-scale systems such as winter storms, tropical cyclones, and severe weather. Oftentimes they get more detailed, but we don't typically have the data go out as far. So if the global model, oftentimes we'll get model data out through 10 days. Not that it's useful at 10 days, but we have it. Oftentimes, more regional models like the North American model only go out to say 3 or 4 days. This input initializes not only the smaller models, the mesoscale models, but it also gives them a starting point for their forecast, just like the global models did for the regional models. And then finally, the mesoscale models, again, even more detail with smaller scale systems such as rain-snow lines in our winter storms. All those are always fun. Supercells and sea breezes can be seen on mesoscale, resolved by mesoscale models. These are often run very much more frequently, sometimes once per hour or more, and can provide forecasts at very high resolution, both temporally and spatially. And then this is a look at when we say high resolution. This is and when I showed the globe earlier with all the grids, and it said that the smaller the grid, the higher the resolution. So this is an idea. The higher resolution equals greater precision, or aka more grid boxes over a given area. So you have, say, this picture here of a 12-kilometer model versus 2-kilometer. So each of these grids on the left is 12 kilometers in width, and each of these grids on the right is 2 kilometers. So you can get a much finer detailed forecast. The higher resolution has smaller grids, so that means it can resolve smaller scale features, like I said, like sea breezes and things like that. So a 12-kilometer model, like the North American model, is a lower resolution than a 2 or 3-kilometer model, like the HRR or the HRRR, high resolution rapid refresh model. All right, was this where, Joe, was this where you
Yeah,
were
we
gonna
can
take it?
hand it off. And actually, you know what I'm going to do, Bryce? We have a few questions on what you presented. So why don't we pause here before we move on to like some of the model output? Just
Okay.
a few questions. From Lisa, what are the biggest sources of uncertainty in the global models? Bryce, I would probably say the observations are
Yeah, I would say the initial conditions are where
yeah,
it all can go wrong or right.
as we say, garbage in, garbage out. But you have to
Yeah.
remember, you know, we have a lot of data going in. So we have our upper air balloons, which are actually a small part. A lot of the data comes from satellites, both the GOES
Mhm.
satellites and the polar orbiters, aircraft. So there's a lot of data going in. But you know, it's not always perfect either. Some of them are estimates. So that's where, you know, you introduce a little bit of error in an observation and it goes up exponentially in the model. So that's, I would say, do you agree,
Yeah,
Bryce?
for sure.
Observations?
Observations are
Okay.
definitely the big
Yeah.
question.
Okay. And we have another one from Krista. Why does the Euro model differ so much from the GFS? That's actually by design. So, in other words, we don't want to have two models that are identical because then you get the same answer every time. So, what they do is we do different equations, different resolutions. Like Bryce was showing all the things about the models. Those are intentionally made different. So, the European model gathers its data. It's called data assimilation in a different way than the GFS does. And that's on purpose because then we'll get different answers in the forecast. So same thing goes for some of the parameters that it does, the way it makes convection or thunderstorms, for example. There's all different types of equations to handle different situations. And by design, they're done differently. So the European Center has done its own research and they've gone down one certain road. With the GFS here in the US, we actually have adopted a lot of what they've done, but there are some differences in the model, we can probably, Bryce, we could go very detailed on, but we won't. But the bottom line is the different models that we have, the European, the GFS, the Canadian, the UK Met, they're different by design because we want to see how they perform in certain situations. So Bryce, do you want to add anything to that?
I think you covered it.
Okay, there you go. And let's see, one from John. Are the lower level models actually fed by inputs to the higher as stated, or do lower levels run from the higher level output? It's kind of on a 3D, so there's really no low level modeling. It's going through different vertical slices of the atmosphere, and as I'll show, some of the models have more vertical resolution than others, so you're getting better, kind of a better forecast that way. But it's also adds to more computing time. So it's a balance between how much you want to give detail and how quick you want to get the forecast out the door. So they kind of feed each other, you know, lower to higher, higher to lower. There's all different types of circulations going on and from all the equations of motion. So just remember, the models are really just like big computers that are solving billions of equations every second. They're just a bunch of equations. That's all they are. And then from that, we can derive all the different output, which I'll get to in a few minutes. So everything kind of works together, if that kind of makes sense. And then John had a question about advancements in accuracy can be expected in the future. I will get to that, John. So in the next section, we'll talk about kind of modeling of the future and where we're headed here in the United States. So I guess I don't see any other questions at the moment. So Bryce, if you want to just keep an eye on the chat box.
Yeah,
Let's
I
see.
can do that.
There are a few in there. Maybe you want to just go ahead and take a look at those, and we can answer a few more of those at the end too, if they look good. Okay, so thanks, Bryce. And now we're going to, second part here, we're going to talk a little bit about some of the model output, and I think most of you are familiar with the different maps, and we'll talk about that, but also something else we call MOS, which is the model output statistics, and that's what you can see on the right. I'm sure some of you are familiar with that, and those are kind of station-based guidance. So on the right, you see an example for Providence from the GFS MOS and the NAM MOS. And MOS was actually developed in the 1960s by the National Weather Service, and forecasts began in kind of 1968. And due to the long history and continuous improvement over the years, it's still one of the most valuable forecast tools. And in my experience in the Weather Service, there's always been talk of discontinuing it, but it performs so well over what we call the raw guidance. So in other words, if you were to look at a map of surface temperature from the GFS model, it's going to have a lot more error than one of these MOS forecasts for Providence. It's just the way it is. The raw model can be too warm at night. It can be too cool during the daytime. But the MOS is kind of statistical guidance that's tied to the observations over the years. So it's got a long database to kind of correct itself. And it's really one of the best performing sources that we have, especially when we get into like a radiational cooling night, when it's clear skies, light winds, the temperature drops very quickly. The raw model guidance doesn't handle that well at all, but MOS does a very, very good job. So it does have its strengths. So we'll give a little overview here of some of the models that we use. First, the global models. Of course, the GFS in the United States, the European model is another one. You can see the time range that they forecast out to, 16 days for the GFS and 10 for the European model. And again, why 16 days? It's not to give us an accurate 16-day forecast. It's to feed climate models that forecast weeks and months into the future. It gives them kind of an initialization. The resolution has gotten a lot better over the years. It used to be up around 30 to 40 kilometers, even 80 to 90 kilometers back when I started in the Weather Service. Now today, it's 9 kilometers, which is roughly, you're talking, 8 miles or 6 to 8 mile. Those are grid points. So in other words, you're providing a forecast at every 8 miles apart, which is a pretty high resolution for a global model. Pretty impressive. Now, also we have the Canadian model and the UK model from Canada and the UK respectively. They forecast out 6 to 10 days and higher resolution as well, 15 kilometers for the Canadian and 10 for the UK Met model, and a number of vertical levels. And again, these are globally based. They're designed to forecast large-scale patterns, over a hemisphere, things larger scale, not getting into too much detail, but the resolution is good enough that they do have some skill for some smaller scale features. But these are really meant in the forecasting side to kind of give you a broad overview of general patterns, trends. But they do, as we know, they do very well in forecasting things like winter storms and thunderstorms in the summertime, also tropical. Then we get into our higher resolution models. The NAM is a regional model, forecasts out 3.5 days or 84 hours. It's a 12-kilometer resolution with 60 levels, and its design is really to focus on to get into those smaller scale weather features. Again, the thunderstorms, the heavy snow bands with the winter storm has skill in that. And on the right, we have what's called the NAM Nest. It's nested into that 12-kilometer NAM. It's a 3-kilometer model. It forecasts out 60 hours. And note, the time range gets shorter simply because the skill is really within that first 48 hours, but it also takes a lot more computation time on the supercomputers. So it's a balance between skill and computational time. So the developers, the modelers have found that that's kind of the best balance, is to go out 60 hours on those really high resolution models. And the United States actually, we have the most number of models to deal with our different weather scenarios. We get more severe weather. We get our share of tropical systems, of course, winter storms. So these are designed to kind of tackle those problems. And then there's other models too. You may or may not have heard about the RAP, which is the Rapid Refresh model. It's a 13-kilometer model, goes out 36 hours. And you can see it's nested. It's got one larger domain, which is almost the whole hemisphere, and then two smaller nests. One is over Alaska, and one is over the continental United States. These are 3-kilometer nests embedded within this larger 13-kilometer domain. So this larger domain, again, feeds these smaller 3-kilometer HER. So they're kind of tied together. Again, Rapid Refresh is the 13, the HER or the HRR are these smaller ones. And the HRR goes also 36 hours at 3 kilometers, and they both have 50 vertical levels. So these are designed for those smaller scale weather features, the thunderstorms, the storm type. Are we going to have supercells? Are we going to have a squall line? The snow bands, sea breezes, anything very localized, small scale. The HER is going to have a lot of skill at, as will the NAM Nest. They're both 3-kilometer models. So then we get into ensembles, and this is kind of where we're headed now and over the next, I'd say, 5 to 10 years, looking more at ensembles. And what we mean by that is we're tweaking things like initial conditions, tease out like sensitivity to kind of change some of the forecast outcomes. So it helps us with uncertainty. Whereas a forecast straight from the GFS is what's called deterministic. This is your answer. Whereas an ensemble can give you more probabilistic information. As you see on the right, we're probably familiar with these hurricane tracks, these spaghetti tracks. These are from ensembles. This is an ensemble solution showing you the range of possibilities for a given scenario. And ensembles, each member has its own unique representation in the envelope of outcomes. So, for example, this are a bunch of plumes, we call them, showing the total precipitation. And each of these plumes represents one ensemble member. And what we can do, we see the range. We have one outlier up here. We have a bunch kind of clustered in the middle. The black line is the mean, and the blue line is the operational run. So we can kind of see how the operational run compares to the other ensemble members, and we can see what the general mean is for all of the ensemble members. And these are especially useful when we get into big high-impact events. Tomorrow is a good example of that. I'll show how we use the ensembles for that. And is there any clustering? Maybe the most likely solution is somewhere in here, clustered here, clustered there. Different ways we can look at the data. Now, the global ensembles, the GFS has 31 members, the European model has 50 members, and the Canadian model has 20 members. And, these weren't kind of picked out of a hat. Again, it goes down to computational resources, how quickly the forecast can be processed, kind of what's the best balance of time versus the number of members for a certain situation. So here's an example from the European ensemble of, it's a seasonal forecast, probability of the most likely category of 2-meter or surface temperature. So it's just showing the various probabilities around the globe. That's one way to look at the data. Then we have the high resolution ensembles. We have one called the SHREF, or the short range ensemble forecast, that has 26 members. And the HREF, the high resolution ensemble forecast, has 10 members. So we're, again, balancing out on the number of members to kind of provide the most skill for a given situation. And these are very useful. We show the HREF for many of our event reviews. We're big fans of it. It's composed of all the members you see here. Different, it's called the WRF model, Weather Research and Forecasting Model from National Severe Storms Lab. There's different cores on the model, an ARW core, an FV3 core that has to do with the model physics. And then we do a time lag too. So we take the current run and then we also combine the previous run from 12 hours ago. So that's a way to iron out uncertainty in an ensemble forecast. Now in the future, we're actually using ensembles to help with severe weather forecasting. And this WARN-ON forecast system is what the National Weather Service is heading towards in the next, I'd say, Bryce, probably 10 plus years. There's a lot of model development going on. There's a lot of test beds going on right now to kind of use this. But this uses output from high resolution ensembles like the HREF and various models to provide severe weather guidance in real time. And the vision is that we will be issuing warnings not by drawing boxes, but by allowing the models or the high resolution ensemble to track along with the storm and automatically keep the polygon, the warning area, moving along with the storm. So that's kind of a different way of providing warnings that we're looking at. Then we have another one. This is called the SCRAM model, but it's actually pretty skillful. It uses the output from the HER to provide severe weather guidance in real time out for about the next 12 hours, as you can see here. It does things like wind damage, tornadoes, hail, all severe. So this is another one that's under development by the Storm Prediction Center. It's another tool that we have for severe weather guidance. And then most notably, we have the National Blend of Models. And this is a very robust, it's its own ensemble. It's a blend of just about every model that's available. You can see them all listed here on the right. It's individual models, it's high-res models, it's ensembles, it's MOS data. It's pretty much the whole kitchen sink. And the point of the National Blend, or NBM, is to eventually have the weather forecast offices begin their forecast by using the NBM. So we have a consistent start to our forecasting. You won't see these seams in the forecasts across the country. So there's development work that's being done now. It's been upgraded several times, and it continues to be upgraded as different members are brought into the National Blend and verification work is done. So it's really providing us with a whole suite of information. We get a deterministic forecast kind of from it, like a most likely, but we also get a range of possibilities. So for example, during the blizzard, we were showing some of the high-end potential snowfall to our emergency managers just to give them a sense that this could be very big, and indeed it was. So This is just all a way to leverage technology, leverage the best model information that we can to provide the most accurate forecast. So day to day, we use the National Blend for our basis for our forecast. It does very well, especially in the extended forecast. It's very skillful. So moving forward, the National Blend will kind of be the baseline for all forecasts in the National Weather Service. And just to show you some examples of that, here's on a national scale. This is a map of high temperatures. You can see, if we were to patch all the forecast office, high temperatures across the country, you might see some boundary issues or some kind of clunky looking graphics. This is all very seamless, as you can see. You've got some below zero numbers up here in Montana. You've got some 70s in Texas and Florida. But this will be a common starting point for our forecasts. And here's an example of wind gusts across the country. You can see higher gusts in some of the Rockies here. It does very well with elevation. It does well over the coastal waters as well, as you can see off the coast of New England. It's a very good basis for our forecast. And of course, snow. Don't want to leave that out too. And you can see, it does give some pretty good detail. If you look out here in the Rockies, the Cascades, it had some pretty good detail to the snow, showing the higher numbers and kind of the higher mountain ranges across the area. So again, this is something that we are working with now. It's under continuous improvement, but I imagine it's going to lead to much more accurate forecasts moving forward. So what's the future? We'll finish up with this. And here's a really busy chart. But the one thing I just want to show you is on the left is kind of what we're doing today. So look at all these models that we have. There's a whole bunch of different models. You may recognize some of them. You may not recognize others. But there's a lot here on the left column. And then what I want to do is focus your attention on the right. Notice how much simpler it is. So what we're doing is, in the future of modeling here in the United States, is going to something called the Unified Forecast System. So what it's going to do is get away from these single, what we call deterministic models, like the GFS or the NAM or the European. And it's going to leverage more towards these ensemble solutions, so which tackle a bunch of different problems. So if you note here on the right, all of the UFS programs that are listed are based upon a different problem. We have seasonal forecasts. We have a hurricane forecast. We have a short-range regional high-resolution model, air quality, coastal, Great Lakes, hydrology, space weather. So all these are geared toward different problems, and then the models are kind of thrown into where they belong. So medium range weather is going to be the GFS ensemble. That would make sense. It's a global model. Short range, regional weather, that's going to be something called the RRFS, which is the Rapid Refresh Forecast System. So think about it as kind of like the HREF, the next version of the HREF. It's going to be a high resolution ensemble. So we will no longer have a model run at 12Z or 12 Greenwich time, 18Z, 0Z every 6 hours. We're going to have nearly hourly runs of this high resolution ensemble to provide constant updates to our weather. So it's really a different way of doing modeling. It's a more efficient way for computing resources. And I think it makes a lot more sense tackling various issues as opposed to just having a whole laundry list of models here that some of them do the same thing and they kind of overlay, what they do. It's just having too many models for too many different things. So this is where we're headed. And as you can see on the timeline, this is fiscal year 25, which would be 2024 to 2025. So we're not too far away from getting there. And, right now we're in what's called a moratorium for model development. So what we're doing is no more new development on the traditional models, the GFS, the NAM. Those are kind of frozen. In other words, they're not making any changes. And now the resources are being put into these newer systems and ensembles. So just kind of giving you a peek of where we're headed in the next few years. But it's definitely exciting to see a lot of the new, computing technology being applied to weather. And, you look at something like this, and then you go back to Bryce's first slide where it took 24 hours, 6 weeks to produce a single point forecast. It's actually pretty amazing. So with that, just I want to remind you, Weather Models 202 on Tuesday, March 1st, we're going to talk about precipitation type and snowfall. This is one of the probably least understood things that come out of the models. And I know everyone gets excited when they see a day 7 snowfall forecast, but there's so much error even in the next day snowfall forecast. So we're going to talk a little bit about that on March 1st as part of Weather Models 202. So I hope you will be able to join us for that. So at this point, we will pause here. And Bryce, we can go ahead and take some questions. We have a few here, and then we'll get on to the weather briefing. We certainly invite you to stay for that. Let's see, Bryce, what do we have? So GFS.
All right.
Oh, I see one from Paul. Let's talk about this. Is a common question. GFS versus Euro, which recently has had the higher level of verification. So I know a lot of times it's very much personal opinion. The Euro nailed this storm. Boy, the GFS did terrible. Oh, the GFS nailed this one. The Euro didn't do good. That's not really how the verification works. What they do is they look at the flow, kind of the flow across the whole hemisphere, and it's verified that way through compared to observations. So I believe, Bryce, and you can correct me if I'm wrong, the top 4 in that order, I believe the Euro is still first. I believe the UK Met now is number 2. They recently upgraded that.
Oh.
I believe the Canadian is 3, and it's very close with the GFS. The GFS has made great strides since they changed the core to what's called an FV3 core, which is just a different core of the model. It's actually done very well. The GFS actually did very well over the tropical season. If you're going to compare storm versus the other models, including the Euro, it did very well. And I will say, with the recent blizzard, I remember seeing a 2-week forecast from the GFS that showed a storm off the East Coast, and it never wavered from that. So it was the first one to actually pick it up. Even though it ended up being too far offshore, it actually showed the potential first. And again, about 2 weeks ahead of time, which is pretty incredible. So, yeah, so I mean, we all have our biases, and certainly there's no one model that's going to be right every time. But overall, if you look at global, verification, and we're talking about like heights at 500 millibars or the 18,000 foot level, that's typically what's done. The European is recently in first, but the GFS is they're all making strides, actually. The Canadian, UK Met, and GFS are all getting closer to the European. So they're all all 4, I would say, are very skillful models, and you shouldn't just discount one because it's not the top. So there's your lesson on that. Okay.
Somebody said that, which this might be, somebody else might have this question too. So, what does model verification mean? What are qualifications to verify? Basically, that just means how well did what actually happened compare to what the model said was going to happen. So if it verifies exactly, then whatever the model forecast is what happened. And if it didn't verify well, then that means that the model was saying it was going to do one thing and something else happened.
Yeah, and it's very this is why we have modelers, because people like Bryce and I, we were not that smart, but they go through things like standard deviation. It's a whole lot of math to kind of do it's not just a simple one-to-one comparison. So pretty complex. There's a question here from Peter, and it's actually a good one. What would you observe on the recent history of the advent of Weather Underground and IBM acquisition of the weather company? Well, I want to talk about different models, because private industry now are running their own models, and that's a really good thing. So IBM has a weather model. Different companies have their own models they're developing, which are kind of the war for weather research and forecasting, which is an open source code, so anyone can run it. So what's happening now with the weather service is we're actually partnering with some private companies to share, kind of best practices with maybe, IBM, for example, has something they're running in their model with success, and they'll share that. So it's actually becoming a lot more collaborative between the government and private industry in the modeling world. And that's just going to lead to better and better forecasts. So just good stuff for the weather community. I'm really excited about that. Let's see. A lot of questions about the Euro being better than the GFS. It's very, I think, again, what you're all talking about is very anecdotal from storm to storm. I can go back and show you just as many times that the GFS was better than the Euro. So my advice for you is just don't fall into that trap. There's no perfect model. So, and a good question from Eric, which is a follow-up. If they differ, how do we choose which one is right? Well, we look at the ensembles. So if, for example, with the blizzard, we saw the European was obviously closest to the coast and was correct. At one point, it was too far inland and was bringing rain to us. But we saw the different ensemble members were all clustered right around the benchmark. So we kind of know, that it's got a pretty good odds of being a big hit. Whereas the GFS eventually trended too far offshore, and as did its ensemble members. So looking at the upper air pattern and just a little bit of intuition and experience would say, yeah, this is a pretty dynamic and strong system. It's probably going to tuck closer to us. So we felt that the European was right, but you also can't discount that more offshore solution. Usually, and the old rule, Bryce, from the Weather Prediction Center is take the average of the GFS and the European for a winter storm, and you'll do pretty well. So I think that still holds true. But it's really just a lot of intuition and based on past experience. So let's see. We got a lot of questions here. Do you have any? Want to pick one, Bryce? And let me just point out, if we don't get to your question, please just shoot me an email, and I can certainly get you an answer.
So somebody asked, do Asia and Africa have models, and would they be helpful to us thinking of hurricanes?
So yeah, Asia, the Japan Meteorological Agency, China, they do, and they do share it. Most of those are focused on that part of the world. And yeah, because obviously the U.S. has interests in other parts of the world as well, especially military, as far as hurricanes and things like that. So there is an international agreement where the countries share model data with one another. That's why we can see the European data and the UK Met. They can see the GFS data, and in fact, I know the Australian Meteorological Agency uses the GFS quite a bit. They've had a lot of success with it. So there is that sharing, Anne. So. And yeah, it is, thinking of hurricanes, things like that, we can share back and forth. And you can find a lot of these models online too if you do a search. They're all available. Let's see, what do we have, Bryce? Well, here's one about Chatham. This is another good one from Ken. So we said, observations are the main sources of uncertainty. So we did say in a previous webinar the Chatham weather balloon is on hiatus because we have to find a new location, which should be done in the next year or two. But have we noticed Boston forecast getting worse because of that? No, actually. And when you look at the radio SONs, it's only about, it's not one of the top things that go into the models. So the soundings are useful, but they're actually better for looking at near-term weather. So like the rain tonight, we can see what the freezing level is doing or things like that. Really, it's the satellite data that is the main player with initializing the models and providing observations, and aircraft data. A lot of commercial aircraft are equipped with weather equipment that transmit back to ground. So weather balloons are a part of it, but they're actually a smaller piece of the overall puzzle. So that's a good question. But no, we haven't. I don't think we've really noticed anything.
No.
On that. Let's see. We're just going to go through. I apologize. We have a lot of people. We have over 100 people on the webinar tonight. So let's see. And again, if I can't get to yours, just please feel free to send me an email. Brian wants to know: is there a website where the NBM can be viewed publicly? Yes. Just do a search, National Blend of Models, and it'll come up. There is a public site where you can view some of the data, and that's being expanded with more and more to look at every day. So absolutely. Here's a good one from Patrick. Is there a dedicated model for local sea breeze prediction? Mass Bay, Gulf of Maine. That is where we actually look at things like the HRR model, the high resolution rapid refresh is good. The NAM Nest is good for that. In the past, some weather offices ran their own local models. I know we had one for a time in the early 2000s, Bryce. We had our own, it was called the ADA model, but it actually did pretty well. But yeah, we've kind of gotten away with that. It's hard to support a number of local models at the offices, but they're being transitioned more to these high resolution, ensembles. So, but there are some universities have their own model too. So you can, if you look online, you probably can find them. Not too far. Let's see. Let's see what we got. So William just wants to know, for the global models, how is the data gathered from areas like China or Russia? Do we rely on satellites? No, they do share their observations. Weather balloons are launched across the globe, and that's all shared through through international agreements. There's a free sharing of weather data, so we do get that as well as satellites. But again, it's largely satellites. Here's a good one from Patricia, and this is actually something we talked about, Bryce. How much error was interjected when the air flights were canceled globally for the pandemic?
Yeah.
There actually was an effect, and it was mostly on flights over the Pacific. Obviously, that's where our weather comes from. There was a little bit of a decreasing skill. I forget what the exact numbers were, but it was shown that the lack of aircraft data did impact some of the forecasts. That's kind of interesting. Good question. And
somebody
Go ahead.
Somebody has a question that stuck out to me because I actually was the one that used this term, this phrase. Somebody said in AFD pre-blizzard, the forecaster utilized the windshield wiper effect. Please explain. That is just referring to the idea that, and it emphasizes the utility of ensemble using a probabilistic approach and looking at ensembles, especially in the several days leading up to an event, because if you when we say windshield wiper effect, sometimes that can be in, say, the track of the storm. So with our blizzards, they are very heavily reliant on exactly where it tracks, and if it tracks further 100 miles, 50 miles, 10 miles to the west versus the east, have a big change on the impacts. So say one run at 8 p.m. takes the low up the Hudson Valley, and then the next one takes it over Cape Cod, and the next one takes it over Hudson Valley. That's kind of the windshield wiper effect of following these one-off what we call deterministic model runs, so where they just run the model once with one set of initial conditions. The output can kind of flip-flop back and forth in a short period of time over, say, 12 hours or to 24 hours. And so as a meteorologist, you're trying to cut through the noise of that flip-flop back and forth and say, okay, to figure out, is this a temporary flip and it's going to flop back in the next run? So I'd probably like to look at the ensembles to see if they're, say 60% of the ensemble members take it up the Hudson Valley and only 40% take it over to Cape Cod, then I would say, okay, there's a better odds of it actually going over up the Hudson Valley. So windshield wiper effect just basically meaning how it can flip-flop back and forth, and if you're just making the forecast based solely on one model run, then you're going to be getting a lot of swings in what is expected.
Yeah, and Bryce, I remember the day before the blizzard, the afternoon run of the NAM actually was a shutout. It took it way offshore and had nothing over us, which was one. Exactly what I was thinking of. Yeah, good point. Okay, and we'll finish up here. We've got one from Sebastian. It's a good question. So, what do you think is the highest reasonable resolution that models could make? And there's actually been a lot of research done on that. And they kind of found for the highest resolution, the sweet spot's kind of that 3 kilometer. And that's why a lot of ours are at 3 kilometers. They've tried 1 kilometer, really, really super high resolution. And there's so much noise in the output that it's just kind of unusable. So they've kind of found 3 kilometers is the sweet spot. And that's what we're using today. And then another follow-up, which is a good point we can talk about, could machine learning capabilities being experimented with be used in forecasting? Absolutely. And that's actually something that's going to be looked at here in the next 5 to 10 years. So for like severe weather, it would be watching, have some radar information coming in. The model will be running and compare it to a past event. And it could tell you in an instant the most likely outcome. The storm is going to strengthen, the storm is going to dissipate. So machine learning is going to be a very, very big part of forecasting here in the next 10 years. So great point. All right. So I think, Bryce, we will stop there.